All right, so we start out here with section 1 of chapter 19, and chapter 19 is all about acids and bases. Now, we say most things can be classified as an acid or base, so this section here looks to identify what we actually can consider on the chemistry side of the house an acid versus what we can consider a base. Okay, now with our acids and our bases, okay, they're going to play not only an important role in our industrial complex and our industry in general, but they're also going to play a role in a lot of biological processes and processes that we use every day. All right, so we start off really simple here, and we start off with some properties. So an acid, and in the chemistry lab, don't ever try anything, but an acid is going to have that sour taste here. Okay, so carbonic acid in carbonated beverage beverages kind of have that sour taste because of that acid. Okay, citric acid, right? Our oranges and our apples, right? They're going to have, again, that sour taste. Bases, on the other hand, are bitter. Now, I definitely wouldn't suggest eating that soap. Our acids and bases can also be really, really useful in identifying the specific pH, right? And that's going to tell if something is an acid or a base. Or if we use an acid, for example, on this rock, we can tell what type of rock it is based on that chemical reaction. So a lot of good uses here, right? So now as we move on here, what happens in an acid and base reaction? Okay, well, I want you to notice a couple of things, all right? The first reaction here produces hydrogen gas, and we see this, but we don't see this as often, at least in the chemistry laboratory, as a reaction between an acid and a base, and this is actually just baking soda and vinegar, the second example here, that produces our H2O as a liquid, and then what we would call our salt. And our salt in this case is that sodium acetate here, first thing listed as our product. But a lot of the time, especially in this type of class, we're going to see the production of that H2O liquid. Essentially, the H from the acid and the OH from the base are going to get together and produce that H2O. All right. So those are kind of some of our basic building blocks that we have. All right. Now, with litmus paper, which we don't use litmus paper a whole lot, but if we did, acids are going to turn the blue litmus paper to turn pink, and bases, you have to have red litmus paper, but it's going to turn blue. You got to make sure you have the correct litmus paper, and it turns the correct color based upon what you have. Acids also can conduct electricity, and we're going to decipher later in this chapter how strong of electric current they can actually carry, but we can describe an acid or base as the ability to be a conductor. Okay, pure water cannot conduct our water because there's no ions in solution, right? So we move over here with this, and we have this chart here. It's kind of nice to see here, and we get an acid versus a base. So if we say we have more acid, or a solution is acidic, there's going to be more hydrogen ions. And I want you to take down below, take a look here. That red part, it has brackets, which just represent molarity, H plus. That is your hydrogen. So that left-hand side, hey, H plus. Well, as you start to have more and more hydroxide ions, you're going to have a basic solution. And then a neutral solution has an equal amount of hydronium ions and hydroxide ions. Okay? Now, in our class, like I said, we deal with a lot of aqueous chemistry. This means we're going to utilize water. Okay, so unless I tell you differently, we are going to utilize water as our particular solvent, the item doing the dissolving. Okay. All right. Now, some other properties of water that we don't think about. Okay. Remember, acids are looking at more H plus hydronium ion in solution than our OH minus. Okay. What actually happens with water is really, really interesting. And we don't actually think about this unless I explain it right here. Okay. So we take a look at this. And this is what we call the auto-ionization of water. Well, what actually happens is this. One of these waters acts as an acid, and one of the waters acts as a base. Now, I want to show you this. All right, let's just say, for example, that this water right here that I highlighted up top is our acid. What's going to happen is this. An H plus is going to get donated from the acid to the base. And what's going to happen is you're going to have our H3O be produced. Okay. At the same time, that H plus, it had to go somewhere, it had to be taken away, and so it forms that OH minus. Now, I also want to take time to talk about this. We are going to see H3O plus commonly just written as H plus. It just saves some time. It means the same exact thing that we have in our particular solution there. Now, with pure water, okay, you may think, okay, well, we produce some H plus, shouldn't we have a pH that's below 7? And shouldn't we have an acidic solution? Well, we don't, because of this. We have the bottom statement here, equal number of H pluses and OH minus, which you remember from that previous slide means that we have a neutral compound, okay? All right, so moving on here, and now we can actually talk about acids and bases. So that was our simple information here. We're going to get more in depth with this. And so we classify acids and bases on a couple of different ways. All right, Arrhenius, all right, again, just a scientist came up with this in the late 1800s. He said that, okay, an acid has to contain a hydrogen. And the hydrogen has to be donated, okay? You have to get H plus in solution, okay? So our example here of our acid would be hydrochloric acid, where that H plus that's sitting out in front would get donated, we call that, or would ionize, and we would see that in our particular solution. A base, in Arrhenius's definition, had to contain a hydroxide. Now, remember, hydroxide is OH minus. Here's the problem. We look at ammonia, and ammonia is actually considered a base. It is a base, but by the definition of Arrhenius, we cannot classify it as an acid or a base. Okay, so there was our problem. Arrhenius gave a very good idea of what could be an acid or base. We just needed a better one. All right. So then we turned to a Bronsted-Lowry acid and base. All right. Bronsted-Lowry said, hey, we need to define items a lot more broadly that can be acids and bases, and so they came up with this model. Okay. A Bronsted-Lowry acid is a hydrogen ion donor, an H plus donor. A Bronsted-Lowry base is an H plus acceptor, or a hydrogen ion acceptor. Okay. lot more items could be classified as an acid or a base based on Bronsted-Lowry's model. Now, there's one other way that we can classify acids and bases, but we save that here towards the end. Now, I want to just talk about this just for example. We have this. Now, HX is not technically a compound, but we can use it for our particular example here, okay? So HX in this scenario is our acid, all right? So I'm just going to label this as our acid. Now, this H plus gets donated, just like we saw before, H plus gets donated to our H3O plus. Gets donated to our H3, or it gets donated to our H2O. And so as a result, H2O gained that extra hydrogen. So now it's not H2O, but now it's H3O plus. Now remember, H3O plus is what we would call our H plus. And what happens here, this X actually should have a negative sign there. What happens is that we form H plus and we form that X minus. Okay, so that H from the acid gets donated. Our water, because it is accepting that particular H, our water, this is our base. Okay, acid donated the H plus, base accepts that H plus, and we demonstrate that with this example here. Now, what we can also do is we can have these items, these terms called conjugate acids and conjugate base, all right? In a conjugate acid, it is the addition of one extra H, and a conjugate base is an addition or the subtraction of one extra H, okay? And so with this here, I want to show a couple examples here, and that is this. We want to identify the conjugate acids and bases in the following reaction. All right. Remember, Arrhenius said that an acid donates its H plus, a base accepts it. All right. So if we look at HF, we find it. On the other side, I say, hey, always try to find something that's really, really similar to F. It's either gaining an extra H or losing. Well, check this out. F minus, it lost an H. This means that the H plus gets donated. The H plus gets donated to the H2O. Okay. Therefore, because HF gave away its H plus, this right here is what we call our acid. Now, F minus, I've already underlined it, but now I want to talk about it. It is missing a particular H. Now, if you look up here, a conjugate base is what happens when we have a species donate its H. So therefore, our F minus here, this is classified as the conjugate base. Okay. On the flip side here, H2O here is H2O. Because it accepted the H, it is considered our base. H3O plus. Remember, I always say, hey, try to find something that either gained or lost just one H. And H3O plus on the other side here, I'm going to highlight this. H3O plus, because it gained that extra H, this is considered to be our conjugate acid. Okay, now go a little bit further, faster through this. NH3, if I look NH3 on the left, well, something similar is NH4 with a 1 plus charge there. It gained one H. Because it gains one H, and that H, just in case you're wondering, comes this time from H2O and gets donated to NH3. NH3, because it gained one extra H, this is actually considered a base. And NH4 plus, because it has an additional H, this would be considered the conjugate acid. Now, this makes it really easy to identify what is the actual acid, which in this case is our H2O. H2O is considered our actual acid. If you look over here, something really similar to H2O is OH with a minus. It lost one H. And so right here, this thing right here is our conjugate base. Okay. Now, there should also be a plus sign in there. But this is how we identify our conjugate acid-base pairs, okay? All right, so H2O, I want you to take a quick note here on this. H2O, in this case, acted as both an acid in that first example, or excuse me, a base in that first example, and then in that second example, acted as a particular acid. Okay, because H2O can act as an acid or a base, it is considered an amphoteric substance. That means it could either donate that H and be an acid or accept another H and be a base. And water is one of those particular examples. Now, there are still other items that cannot be classified as acids or bases, even with the Bronsted-Lowry acid or base name. Okay, we have a lot of substances that can, and this is just a small chunk of items that can be classified as a Bronsted acid or base based on the properties that we have. But there's still some things that just cannot be classified as a Bronsted-Lowry acid or base. Okay, so we have our final model to indicate that we have an acid and bases, and that is this. Our Lewis model of acids and bases. This is a little bit different. Lewis acid is an electron pair acceptor. A Lewis base is electron pair donor. Okay, and I really like this chart here. Everything that we've talked about in terms of acids and bases is summarized right here in this particular chart. All right. So now, if we take a look at this. And I don't spend a whole lot of time on Lewis acids and bases. It's really a way to classify organic chemicals as either acids or bases because sometimes they don't have that H plus donate or accept. Okay. Now we get into some final terminology here with this section and the different types of acids. All right. So we have a monoprotic acid. Mono, if we just break it down here, just means one. Well, if it's monoprotic, that means there's only one H plus that we can actually donate. So up to this point, all of those things that we've seen, these items right here can only donate that one particular H plus, okay? All right, so if we take a look at this, HF, there's only one H total to donate, okay? So there's only one of our H's to donate. It's a monoprotic acid. Acetic acid, yeah, you see that there's multiple H's, but only one can actually be donated. And because only one can be donated, it's considered a monoprotic acid. Last point here is this. Benzene here, it can't be an acid or base. Yeah, it has H's, but those H's, the way it's structured in its formula, they're locked into place. They cannot be donated. Okay, so it can't be classified as an acid or a base. It can't actually even accept those particular, in most cases, can't accept those H pluses. Okay, so benzene cannot be an acid because there's no H to donate. All right. If we have things that can only donate one hydrogens, we can have items or chemicals that can donate multiple. And this is what we talk about, a polyprotic acid. All right. So a polyprotic acid can donate more than one H. All right. This only happens in a couple of our acids here. For example, we have sulfuric acid and we have phosphoric acid. Notice here, these H's out in front, are the ones that can be donated. So sulfuric acid can donate 2, phosphoric acid can actually donate 3 total hydrogen, all right? So final point here about our acids and bases is this. We have some substances which are called anhydrides, which they say by definition are oxide compounds that can be acids or bases if they're added to water, all right? This, for our class, a little bit difficult to understand, but if we have something like carbon dioxide, it gets added to water and via chemical reactions there, it forms carbonic acid. Well, carbonic acid, again, acid in itself, those 2 H's can be donated, or what we're later going to call ionized, to form those H+, all right? Now, bases can also happen here. So we have calcium oxide. It gets added to water, and it can also form, it should not be H2CO3, but this, I want you to cross this out here. This should actually be calcium hydroxide. Okay, calcium hydroxide would be CaOH2, and that right there is what we consider a strong base. All right. Again, some other examples can do very, very similar items there. Okay. So again, all this section did was give us a little snapshot of our particular acids and bases. It helped us classify, okay, how can we say something is an acid versus a base? And as we progress in this chapter, we're going to see those models exist, how we can classify them, and introduce that concept of our pH.